The title of today's lecture is Flash-based SSD. Solid-state storage device. It does not have mechanical or moving parts. It is not like HDD and
transistors.
it retains information despite the power loss, unlike typical RAM. So in this lecture, we're going to talk about the NAND flash-based SSD. Most of the storage devices in current computer system is equipped with NAND flash-based SSD. That include notebook or smartphone or your smartwatch, and even in the server. So we're going to talk about the details of NAND flash-based SSD. There are two important characteristics of NAND flash-based SSD. In NAND flash device, to overwrite a given piece of the information to the NAND flash SSD, you first have to erase a bigger chunk. So we're going to talk about the details of these properties later. And the number of erase write is limited. So these are two basic characteristics of the NAND flash-based SSD. Flash memory consists of an array of cells, and each cell contains electrons. And programming a cell consists of removing the electrons out of the cells. So depending on the amount of electrons stored in each cell, it can represent 0 or 1. So for single level SLC NAND, each cell can represent 1 bit. So it can represent 1 or 0. Multi-level cell is a NAND flash device that can contain 2 bits for each cell. And there are TLC, QLC, and even PLC. So as you can see, for a single level cell, there are 2 voltage levels between 1 and 0. So these two informations are far apart. And then for MLC, for the same voltage range, it is partitioned into 4 ranges. And depending on the voltage level of current cell, it can represent 1, 1, 0, 1, 0, 0, 1, and 0, 0. For TLC, it can represent 3 bits. And for QLC, with a single cell, it can contain 4 bits. So as you represent larger number of bits, the total number of information that can be stored in the same number of geographic area increases, which means that NAND flash is getting cheaper and cheaper. This is a structure of flash. There are 2 important concepts in the structure of the flash. First one is block, and second one is page. So block is a unit of erase, and page is unit of read and write. So as you can see, a block is a set of pages. So normally, depending on the flash manufacturer, the page size ranges from 4 kilobyte, 8 kilobyte, or 32 kilobyte, depending on the flash product. And then the block is size of the block ranges from 2 megabytes to multiple megabytes. This is the structure of flash SSD. It first have interface. It connects the SSD device to a host computer like CPU. And then each flash memory SSD has a certain amount of DRAM and embedded controller. And then there is a flash memory, array of flash memory, and there is multiple channels here. and each channel has its own flash controller. So this is the structure of flash-based SSD. So when a host sends a request to write multiple blocks, then the embedded controller here distributes incoming request. First, it transfers these data blocks to DRAM, and then later, with the write-back cache replacement algorithm, it writes those blocks to multiple channels in parallel manner. That's how the write operations are distributed over a multiple flash memory. There are three basic operations in flash memory. First one is read, second one is write, and third one is erase. Remember, in hard disk drive, there are only two basic operations, read and write. Now we have three, read, write, and erase. And read and write is performed in page unit. So it is here, page is its flash page. So in flash SSD, basic unit of read is page, which is usually fixed, and normally these state-of-art SSD has like 8 kilobyte page size or 16 kilobyte page size. It is determined by the flash product. And a write operation, it is also called a program. So write is performed in page unit, and flash memory is all initialized to 1, and writing a page or programming a page is process of transforming certain one value to 0. And erase operation is an operation of initialize the flash block, and it is performed in block unit. So block, as we mentioned before, block is an array of pages, and usually it is determined by the hardware and determined the flash product. For some product, for example, 256 pages. And if you assume, for example, the page size 4 kilobyte, then block size corresponds to 1 megabyte. Okay, so erase is an operation of transforming a value 0 to 1 in block unit. So let's consider this is a single page, for example. And then writing this value is equivalent to transforming a certain value of 1 to 0. And when you write another value to the same page, 0x, if 0, the bit pattern corresponds to 1, 4 ones, and 4 zeros. And if you try to write 1 1 1 1 0 0 0 0 over this flash cells, then what you have to do is you have to convert the value 0 to 1 and value 0 to 2. And that is not allowed due to the nature of flash memory. So this is not allowed. So you cannot overwrite a flash page, which means that you cannot convert the value of 0 to 1. To do that, you first have erase the block. Okay, you have to perform the erase operation, which means that you have to initialize the entire flash page, which means again that you have to convert all the values in the flash cells to 1. So that's what we call erase operation. So erase operation is something like erase the contents of what you've written on the paper. So that's precisely what erase means. This is another example of writing a block. So for example, here we'll write 2 pages, page 1 page 2. And when you perform write, you cannot overwrite the existing pages, and you have to write in append only manner. So here you've written 2 pages. When you write another page, you have to write to the flash page that has not been written before. Okay? And the operation of erase is make the entire block clean and set it to the initial phase, like this. So this is write, and this is erase. So remember, in flash memory, you cannot overwrite because it takes lots and lots of time to transform a value 0 to 1. So to do that, you first have to erase the entire block to write some pages. There is some issue you have to be made aware of. That's reliability. First, the flash memory wears out. It's like a paper. So if you write something with a pencil and then erase again, and write something with a pencil again and erase again, and then you write, if you repeat, erase, and write, then eventually the paper wears out, and maybe if you do it again many times, then the papers will be torn out. Same thing happens to the flash memory. So flash cells wear out as you program and erase it. And eventually, finally, the block becomes unusable. So we call it an EW cycle here, EW cycle. And typical erase wear cycle for MLC-based block, EW cycle is 10,000. For SLC-based NAND, the PE cycle is 100,000. Next thing is disturbance. When accessing a particular page within a flash, it is possible that some bits in the neighboring page may get flipped. That's very interesting phenomenon. So, for example, if you read a cell, if you read the cell, let's say if you read this cell, then operation of reading this cell may change the status of neighboring cells, these cells. That's what we call read disturbance. If you program this cell, it is also possible the neighboring cell is affected. That is called program disturbance. The flash memory should be updated in out of place manner. So the basic reason for out of place update in flash memory is the flash memory should be erased before overwritten. So for that reason, flash SSD uses out of place update for write operation. Let's consider following scenario. There is block 1, and all blocks are clean. It's fresh. And then an application likes to write to sector 1. Then because sector 1 is clean, then it can write whatever contents it has to sector 1. We call it an in-place update. However, application wants to write to sector 1 again. The sector 1 is already written, so we cannot overwrite. So what you have to do is you have to erase sector 1 before write, but it takes too much time. So as a result, what flash memory do is write whatever contents to the next sector, and then mark it as a sector 1, and mark it as this is the valid sector 1. So that's what we call out of place. So this is the basic rule for updating the flash memory. There is a key piece of software in the SSD controller that is called Flash Translation Layer, and we usually call it an FTL. FTL is a software that makes the SSD look like the HDD. It performs three essential tasks. Address translation. So FTL is responsible for locating the requested block from the host. And the second one is where leveling. The third one is garbage collection. So for address translation, when the request arrives from the host to the SSD, for example, write to LBA10, then FTL is responsible for finding where the actual location of the LBA10 is. And then next one is where leveling. FTL should try to spread writes across the blocks of the flash. That's because the EW cycle for flash cell is limited. So if FTL has to be careful on avoiding writes are centered on a specific flash memory strips or cells. The third one is garbage collection. So we're going to talk about it later. So this is the I/O stack of the SSD-based computer system. There's an application, and the application sends an I/O request to the file system. And then this is SSD. SSD has flash memory and controller and everything, and on top of it there is an important piece of software called the flash translation layer, which is responsible for three things again: address translation, well leveling, and garbage collection. In legacy computer system, file system is issuing an operation of reading or writing. And then when the request arrives at the hard disk drive, then they accept the read request and write request and performs the task. But flash memory is slightly different. File system still uses read sectors or write sectors. However, in flash memory, there are three operations: read page, write page, and erase block. So there is discrepancy between the existing hard disk drive and SSD. So to fill the gap between these two discrepancies, they introduced a notion of flash memory. FTL. So here, FTL sits. There comes FTL, and the flash translation layer is responsible for make the flash memory-based SSD look like HDD, and make the SSD compatible with the legacy software. That's the basic role of the FTL. So let me provide an example of how the translation, flash translation works. When writing a page to the flash SSD, we append the write to the next free spot. Free spot means free page. In the currently being written to blocks, we call it active block. For example, if we start to write 4 pages, and the contents corresponds to A1, A2, B1, and B2, and those pages are written to the first 4 initialized blocks. Here, we schematically illustrate the structure of an SSD. There is a flash translation layer, and in the flash translation layer, there is mapping table. Mapping table is data structure to it's something like page table. Page table means that where the page table means the location of the physical page for a given logical page number. That is the same for the mapping table. When a host requests for a certain logical block number, the mapping table represents mapping table contains the information about where the physical location of the given logical block address is. There's controller, and there is blocks, block 0 and block 1 and block n. And in this example, each block contains 32 sectors. Okay, and so when we perform erase, then we erase the entire block. So we erase the 32 pages or 32 sectors at a time. Then mapping table, it contains a pointer to the active block. Active block is the block where the currently incoming writes needs to be written to. So let me provide example. Let's say that page size is 4 kilobyte, and then a block is small, a block of a flash block. A flash block consists of 4 pages. So we are writing the 4 pages, and 100, 101, 2000, 2001, and then the contents corresponds to A1, A2, B1, and B2. And then the initial state of SSD with all page marked is invalid. So this is initialized. This is basically empty. At the first phase, we erase 4 pages. We erase 4 blocks. And then so the block 0 is now writable. We program the pages in order and update the mapping information. So first page we are going to write is page 100, and then we're going to write A1. Okay, and then because the page 100 was written to the page number 0, so the mapping table contains an information about this. 100 is maps to 0. And then we perform 4 page write. So we write at LBA 100 A1, LBA 101 with contents A2, LBA 2000 with contents B1, and LBA 2001 to contents B2. So these contents are written in order to the block number 0, and in the mapping table, mapping table contents are set to properly represent the location of the actual pages where the request has been written to. For example, the LBA 100 has been written to page number 0 in block number 0, and of course in the second page, LBA 101 has been written to the page number 1, LBA 2000 has been written to page number 2, and LBA 2001 has been written to page number 3. So the mapping table that contains information about where actual location of flash page is updated as follows. Let's consider the situation, the garbage collection. We update the block 100 and block 101 with the content C1 and C2. So this is an update. Okay. Then because all the blocks are written in append-only manner, the new contents for block 100 and block 101 will be written to the new blocks, block 04 and block 05. So, as a result of writing these blocks to the flash memory, the mapping table has been changed to this. So, block 100 will be saved at page number 4, and block 101 will be saved at the page number 5. And then the pages that contain the obsolete contents will become garbage. We call it a garbage. So these 2 blocks have become garbage. So these garbage pages must be reclaimed for a new write to take place. Let's look at the details of address translation. This is sector number 3045, and if we refer to the sector 3045, then mapping table says that it is stored at the block number 125 and at offset 29. Okay, so you successfully did that. And then when you update the same page again, for example, you update here, you write page number 3045 and you update page 3045 again. And then in that case, somehow the flash controller finds a new block, and the new block it has found is block 237 and page number 4. And then mapping table has been updated to 237 block number and then page number 4. So this mapping information has been updated to this. So the role of the address translation is to find the physical location of a given page or given sector. Garbage collection is the process of finding garbage blocks and reclaiming them. So there are 4 basic processes. Find a block that contains one or more garbage pages. And then you read in the live pages from that blocks. Then write out those live pages to the next writable pages, and then reclaim the entire block for use in writing. So this is garbage collection. As you update the request data, some blocks becomes invalid here. If you want to update the contents in this page, then you write new data block here, and then this contents becomes invalid. Okay, so you keep doing this write operation again and again and again. Then many of the pages in a block becomes invalid. And the SSD controller FTL detects that there's gonna be a lack of free space pretty soon. Then the FTL decides to perform garbage collection. What garbage collection does is that here there is empty block C, and then the FTL chooses 2 blocks as a victim for garbage collection. And then what it does is it migrates the valid entry from each block to the flash block. Okay. This one goes here and goes here and goes here. And also, there are 3 valid pages in the block B. So the valid pages in block B also get migrated to block C. 1, 2, and 3. And as a result, all the valid blocks from block A and block B has been migrated to block C. So after doing that, you erase those 2 blocks. So as a result of garbage collection, you freed 2 blocks and you use up 1 block. So this is garbage collection. As you can see, the garbage collection is very expensive. You have to copy the valid pages, and then you perform erase operation on the 2 physical blocks. So garbage collection is expensive. It requires reading and rewriting of the live data. So the ideal garbage collection is reclamation of a block that consists of only dead pages. If all pages are dead, okay, let's say there are 4 pages and all are dead, then you don't have to copy or you don't have to migrate any pages at all, and then you can simply erase it. So that's the ideal case. So the cost of garbage collection is the amount of data blocks that are migrated. And what you have to do is you have to do your best to make to minimize the number of valid blocks associated with the garbage collection. So the only way to minimize the amount of valid blocks, valid page in garbage collection is to postpone the garbage collection as much as possible. because that you increase the chance of making some blocks invalid. So to do that, you provide extra flash capacity. We call it over provisioning. And another way of hiding the cost of garbage collection is to run the garbage collection in the background. The size of page level mapping table is too large. It takes 1/1000th of the SSD size. For example, with 1 terabyte SSD with 4 byte entry for 4 kilobyte page, then you will require 1 gigabyte of DRAM for mapping. So many people has come up with a new idea to reduce the cost of the mapping table size. It is block-based mapping, or we call it block mapping. Or hybrid mapping, or page mapping with caching. In block mapping, we map a block at the block granularity. So in mapping table, it consists of from logical block to physical block mapping. So each entry represents a block number. In block mapping, it suffers from the small write problem. When a small write occurs, the FTL must read a large amount of live data from one old block and copy them into a new one. So let me provide an example. Let's say that we are going to write logical blocks 2000, 2001, 2002, and 2003. And they are mapped into the same flash block with different offset. Then what FTL does is to record that chunk 500 to block 0. So in block mapping, logical block 500 is mapped to the block 0. And then subsequently the 4 pages are written to these pages A, B, C, and D. Now, the logical block 2002 is updated with the content C prime. In the previous slides, block 0 contains all 4 pages from 2000 to 2003, because in this mapping called block mapping, the relocation is performed on block granularity. So because the logical block 2002 needs to be updated, then all the 3 other pages that resides at the same block needs to be migrated together. So when the block is updated from C to C prime, then we have to migrate all the rest of the pages in the same block to the other blocks. So this is the problem of block mapping. So FTL must read in 2000, 2001, and 2003 and write out all 4 logical blocks in a new location, and also we have to update the block mapping table. So it was previously 0, now it's being updated to 4. 4 means the starting page number of the physical block. So this 4 means the starting page number of the block number 1. So in the block mapping table, we record, for each chunk, we record the starting page number for each block to designate the physical block number. There comes a brilliant idea called hybrid mapping. In hybrid mapping, FTL partitions a set of physical blocks into 2. There is log blocks, there are data blocks. And log blocks are page mapped, and data blocks are block mapped. So in hybrid mapping, FTL maintains log block and data block. When an FTL looking for a particular logical block, FTL will consult the page mapping table first, and then block mapping table second. That's because some page might be residing in both data block and log block. Let me provide an example. Let's say there is data block here, and then there is some valid pages. this page, this page, this page, and this page. And then when we overwrite the existing valid block, when we overwrite the existing valid page, we make an update at the log block. If you perform write, then we perform write. Data is written to the log block, like this. And then, of course, the existing valid block needs to be invalidated. This figure shows an example. In the following situation, the logical chunk, which is a set of flash pages, is mapped to the block that starts with page number 8. Okay, so there is A, B, and C, and D. In hybrid mapping, there are two types of pages, two types of mappings. Block mapping for data table and page mapping for log table. So now in this situation, we are going to update these pages with A, B, C, and D. Then, because we are overriding the existing pages on the data block, FTL write them to the log block, and FTL updates the page mapping information as follows. So originally, the block that starts with page number 8 contains A, B, C, and D. Now, for this block, there is a matching log block that is maintained by the page mapping. So if you write A prime, B prime, C prime, and D prime, then it is written to the log block as follows: A prime here, B prime here, C prime here, and D prime here. And this log block is maintained by the page mapping table. So the log table contains 1000 is stored at the page number 0. This is physical page number. And 1001 is stored at physical number page 1. And 1002 is stored at page number 2. 1003 stores at page number 3. Okay. All right. So this is how the pages in the hybrid mapping is updated. So as at the beginning, I have mentioned that there are small number of log blocks, and there are a bunch of data blocks. And log blocks are maintained by the page mapping, and data blocks maintain block mapping. So that's the difference. So when a certain data block is updated, FTL designate one log block for this data block and update these log blocks in page mapping manner. So this is how it works. However, if you keep updating this contents and data block, then the log blocks here is going to be full. Then we have to merge these two. This operation is called merge. So in hybrid mapping, merge is an essential operation that merges the data block with the associated log block. When the log block is full, and we have to perform merge with the original associated data blocks. So in merge, we have to first copy the valid blocks from data block to the free block, and then we copy the valid pages from the log block to the free block as well, and then we free the matching data block and log block. So this is what we call merge. The first thing you have to do is, first type of merge, which is easiest merge, is switch merge. In the previous example, we have updated all 4 blocks for the data block So the log block is full. And then we just switch the log block to the data block and the original data block to be free. Let me go back to the few slides back. Go previous page here. Originally, this was a data block, and then we have updated 4 pages to this A prime, B prime, C prime, and D prime. Now the log block is full, and then log block contains the valid pages in the original data block. So now we are making this block as free and convert this log block as data block. This is what we call switch merge. Go back to the next slides. And then, however, this is ideal situation, but life is not that easy always. And this is the schematic representation of switch merge. So make the data block free and transform the log block into the data block. So that's switch merge. That's easy. However, what if the partial contents is updated like this? So clients overwrite logical block 1000 and 1000 partially. Okay. And then FTL writes the logical block 1000 and 1001 to the log block. Okay. So page 1000 and 1001 is written to the block physical page number 0 and physical page number 1, with contents being A prime and B prime. And then still the chunk 250 is mapped to the physical block that starts with the page number 8. So here all the 4 pages valid. However, this one is the real content that contains the most recent copy of the data, and this is the one that contains the most recent copy of the data. So when the search or read request comes, the read request for page 1000 should be mapped to this region, and then read request for 1001 should be mapped to this region. So that's why when reading or when we perform address translation, hybrid mapping should consert the mapping table for the log blocks first, and then data blocks next. So however, let's consider that the application has updated page 1000 and 1001 again with A2 prime and B2 prime. Then what will gonna happen is we're gonna write A prime, A2 prime, and B2 prime here, and we are going to update the mapping table to 2 and 3. Now the log block is full. We have to perform the merge. So it is called partial merge. Partial merge is the one that merges the data block to the log blocks, like this. So data block is mapped to the same region with the free block, because data blocks are maintained by the block mapping. So the relative offset of the pages in the data block should be maintained at the same value. So it's copied like this. And then log block is copied to its original location. And then after merge, they turn the free block into data block, and then free both data block and associated log blocks. So we are consuming one free block, and we are obtaining 2 free blocks. So we're getting 2 free blocks, and we consume 1 data block. So delta is 1. So it's profitable. Let me summarize the switch and merge. So first one is switch merge. In the first one, data block and the log block. And data block, log block contains completely valid data, and data blocks page are all invalid. So data blocks becomes free, and log block is transformed into data block. That's what we call switch merge. And the second one is switch copy. In that case, the contents of the valid pages in data blocks are simply copied to the log block. and we update the map, and then we free the data block and transform the log block to the data block. This is what we call switch copy. So in switch copy, the merge is performed by simply copying the data block pages into log block. And BAST is a name of block associative sector translation. This is called BAST, but you don't have to pay attention to the abbreviation, what it means. This is hybrid mapping. Here, there's data block and log block. So we select the free block and copy the data block to the free block, and also we copy the data block from the data pages from log block to the free block. Yes. And then the free block becomes data block, and then the data block and the log block becomes free as a result of merge operation. Next topic is page mapping plus caching. In case page mapping table is too large, we only cache a subset of page mapping and leave the rest of them at the storage device. So in page mapping plus caching, we cache only the active parts of the page mapped FTL in memory. So if a given workload only accesses a small set of pages, then translation of those pages will be stored entirely in the memory. So in page mapping plus caching, it exploits locality of accesses. So if we exploit properly the caching, then performance will be excellent without high memory cost. However, the probability of cache miss is not zero. So the overhead of cache miss exists. So in modern SSD, the page mapping with caching is rarely used. So flash vendors tries to load entire mapping table on the memory to minimize the access time. Anyway, this is called page mapping plus caching. In flash memory, there is important characteristics. Flash memory can be written or erased only in limited number of time. So the EW cycle is limited in flash memory. If EW cycle is skewed, which means that certain flash blocks are written a lot more times than the others, then it affects and shortens the lifespan of the entire flash storage. So all blocks should wear out at roughly the same time. So this is the EW cycle distribution. And this is block number. Then what you'd like to get is we like to evenly distribute the block numbers, we like to evenly distribute the EW cycle over all block numbers. So however, a block may consist of cold data. The cold data means that the block may host the executable MP3 files, video files, and stuff. And these files are rarely updated. On the other hand, some other blocks may contain log file or temporary buffer. Then the blocks that contains log file and buffers, they will be updated very frequently. And so the FTL has to periodically read all live data out of such blocks and rewrite it elsewhere. That's what we call wear leveling. Wear leveling increases the write amplification of SSD and decreases performance. That's for sure, but in the long run, it is intended to extend the lifetime or lifespan of flash storage. This is sample policy. Each flash block has EW cycle counter. So in flash memory, it would like to maintain the difference between maximum EW cycle and minimum EW cycle under a certain threshold, or under a certain policy, it'd like to maintain a maximum EW cycle and minus minimum EW cycle divided by the maximum EW cycle is less than a certain threshold. So this is well leveling. Flash-based SSD are everywhere. It is being used by laptops, desktops, servers, smartphones, smartwatches, and even, black box in our car. Flash translation layer is essential component in the SSD. It is used to make the SSD look like a legacy SSD. The essential feature of flash translation is address translation, well leveling, and garbage collection.